So welcome back, and in this short video we're just going to be looking at calculating the waters of crystallization, and then we're going to look at a short experiment to find the waters of crystallization experimentally using hydrated copper sulfate. So we're on page 17 of your notes and we're looking at the formula with waters of crystallization. Now, anhydrous copper sulfate can be used as a test for water, and the reason for this is this reaction here is actually reversible, and you will turn white anhydrous copper sulfate into blue hydrated copper sulfate with the addition of a small amount of water, and you're going to see that later on in the video. And we're going to look at some examples of calculating the formula of hydrated salt. Now this is exactly the same as the kind of calculations we were doing in the last video when we were looking at empirical formula. The only difference is instead of using the relative atomic mass, we're going to use the relative molar mass because we're looking at compounds or molecules rather than individual atoms. So I've got 5.4 grams of hydrated, that means it's got the water attached to it, iron 2 sulfate. But I don't know how much water I've got attached. We're basically heating it to drive off the steam, and the mass of the residue, once I'd removed all the water, was 2.95. So the mass of the water is going to be the mass of the hydrated, take away the mass of the anhydrous, and that's going to give me the mass of my water. So I've got the mass of my iron 2 sulfate and I've got the mass of my water. And they're going to work it through in exactly the same way as I did before with the empirical formula calculations, but this time instead of using the RAM, I'm using the RMM. So iron 2 sulfate has an RMM of 152 grams per mole and water has an RMM of 18. So then, dividing through by the smallest, I get a 1 to 7. So that means for every 1 mole of iron 2 sulfate, I have 7 moles of water. So my formula there is iron 2 sulfate dot, just means it's got waters of crystallization, and I've got 7 waters of crystallization. So this time I'm going to look at hydrated calcium sulfate. So I've got calcium sulfate with some waters attached to it, and I'm going to do the same calculation as I just done previously. So I have calcium sulfate and water. So the mass of my calcium sulfate without the water is here. It is 1.492. The mass of the water, so the water is equal to the hydrated crystals, 1.886, take away the mass of the anhydrous crystals, and that will give me my mass of my water, 0.394. So I'm going to put that one there. Now the RMM, well the RMM of calcium sulfate is 136.2 and the RMM of water is 18. I'm going to divide to find the number of moles. So I get 0.010954 and I get 0.02188. Dividing through by the smallest, which is this one, I get a 1 to 1.9998 ratio. In other words, I've got a 1 to 2 ratio. So the formula is CaSO4.2H2O. And my next example is done in exactly the same way, only this time I'm using RAMs for the sodium, carbon and the oxygen, and I'm using the RMM for the water as 18. But it's still a 2 to 1 to 3 to 10 ratio, so I have there my formula Na2CO3.10H2O. So before we have a look at the experiment, we need to be thinking about what we mean by errors, an experimental error. So an experimental error is an inaccuracy in the results of the experiment which is caused by a limitation of the method or the equipment being used. And there are two main types of error. Measurement error, which is due to the error of the equipment. And this can be quantified. In other words, we can put a number on it. We have a little formula down here which will help us work it out. So our percentage error is our error due to the equipment. So for example, a measuring cylinder has an error of 1 centimetre cubed and a pipette has an error of 0.5 depending on the type. The number of measurements divided by the total measurement. Now there are ways to reduce the measurement error. One is to use equipment with a more precise scale, so using a pipette rather than a measuring cylinder. And the second way is by increasing the total measurement. So a larger mass or a larger volume will give us a larger total measurement and therefore a smaller percentage error. The other type of error we can come across is what we call procedural errors, and these are method errors. Now these can't be quantified, we can't put a number on them. It could be things like estimating the amount of heat losses to the environment in an energetics experiment, or judging the precise moment a substance changes colour in a rate equation. Hopefully by repeating and taking an average, we can reduce these procedural errors. Okay, so I have got my blue copper sulfate crystals and I've weighed out approximately 1 gram of them. I need to weigh this out accurately, but I don't need to have exactly 1 gram. So I've got there 1.1 grams and that's absolutely fine. And you can see there they're a nice blue colour and they're a regular crystalline shape. I've now got my Bunsen burner, tripod and clay triangle set up. And I'm just going to gently heat my crystals in the crucible. Okay, so I've got my Bunsen burner set up and I'm just going to light my Bunsen burner and I'm going to heat my crucible on a blue flame. I don't want to heat it on a roaring flame because I'm not looking to decompose the crystals, I'm just looking to drive off the water. So I don't want a sooty flame which will turn the bottom of the crucible black. And I don't want a roaring flame because that would risk decomposing rather than just driving off the water. You can see there I've been heating it for a few minutes and they're starting to turn white around the edges, showing that they're starting to lose their water. I've now finished heating them and they've turned into a white powder. So this is anhydrous copper sulfate. So comparing the beginning and the end, so we started with these nice blue regular copper sulfate crystals. And what we've ended up with is this white powder of anhydrous copper sulfate. You can see there it's a very powdery version rather than the nice regular crystals we get with the hydrated copper sulfate. Okay, so there are my white anhydrous copper sulfate. And to that I'm going to add a couple of drops of water. And you should see it immediately turns blue. Adding water turns it back into the hydrated copper sulfate, which as we all know is a nice blue colour. That's quite an exothermic reaction, but it's turned the white anhydrous blue. So I've got my calculation here and I'm doing this in exactly the same way that I did the calculations on the previous pages. I've got my mass of my anhydrous residue and I've got the mass of the water that I've driven off, and I work it out in the same way. And it comes to a 1:6 ratio. Now that's a little bit high. I was expecting to find 1:5. I can work out my errors of my equipment and they're quite low, so it's unlikely to be a measurement error that is the problem. So the measurement errors don't actually provide me with enough difference from my data to the data book to account for the error. It's likely to be an error in the method itself. Now if the value for X is too low, it suggests that not all the water has been driven off. If the value of X is too high, in this case this is what I've got, it could be that I've lost crystals due to spilling out of the dish or sticking to my spatula as I was giving it a bit of a stir. So that's the last bit in this video. So we've looked at working out waters of crystallization, and we've looked at the practical of finding the waters of crystallization for copper sulfate. In the last video, we're going to be looking at finding the formula of magnesium oxide and the errors that are associated with that method. But until then, take care, stay safe. Bye-bye.